Okay. My name is Anna. I work at the University of Zagreb in Croatia, and I'm going to talk about native SeND kernel API for BSD. SeND stands for Secure Neighbor Discovery, and that was my Google Summer of Code project in 2009. And my mentor was Bjorn. Okay, before going into details about the protocol, I have a slide that is describing the problem statement for all of you who are maybe not familiar so much with IPv6. So I'll try to give the example of the problem that's happening with IPv4 that I'm sure that you all faced. And there's the problem of default router impersonation, either due to user misconfiguration, so basically someone connects to the network and just by accident configures default router's address, or either due to different viruses that are meant to steal default gateway address, so what they do is ARP folding or just cause any other issues. So with IPv4, what is done, and there is not much that can be done. All the solutions that could be done with, for example, this problem that I've just said should be really low, somewhere close to the hardware level. But with IPv6 in ITF there are specified enhancements to neighbor discovery protocol, and that's what I'm going to talk about. This slide is basically here because I'm trying to make you interested in the whole topic, so that you don't think that SeND is just one of IPv6 nice to have features. It really solves the actual problem. On the next slides, I'm going to give a brief introduction into neighbor discovery protocol. I'll first start with a few words about IPv4 link local communication, so for all of you that are not so into IPv6, and then go just shortly to neighbor discovery and then secure neighbor discovery. And then I'm going to say a few words about my implementation of native SeND API. So on IPv4, link local communication is basically supported through address resolution protocol and a bunch of ICMP-based mechanisms. Two that are essential for the link local communication and most widely used are router discovery and redirect, where router discovery messages and they deal with the configuration of hosts with IP addresses of their neighboring routers, and redirect messages that they basically enable routers to inform hosts about the best alternate route to their destination. There are also a bunch of other ICMP-based mechanisms that are used in IPv4, but they're specified, but they're not usually required by the specification to be used in IPv6. They're not widely adopted, they're not widely implemented, sometimes they're not even interoperable. That's basically because link local communication in IPv4 was specified over many years in ad hoc manner, and that was a good lesson for IPv6. So in IPv6, people decided to write a single specification, single protocol to cover all this protocol that we use in IPv4. And that's basically neighbor discovery protocol. So neighbor discovery protocol is roughly covering address resolution protocol and a bunch of other ICMP-based mechanisms. But neighbor discovery is not just the rewrite of those IPv4 protocols, but it also people also made many optimizations, enhancements of previous mechanisms. I can give some examples of optimizations. For example, with address resolution protocol, when node was sending a query in order to resolve the address, query was sent to all nodes at the network, while with neighbor discovery protocol, a message is sent only to the destination, to the specific host, so we don't flood the whole network. And there are other like bigger changes. For example, the conceptual change with in IPv6 is that all link local communication is ICMP based, which means that the whole concept is pushed a bit up the protocol stack, which means that we can use generic IP layer mechanisms, for example, to generic IP layer authentication or security mechanisms for the link local communication. A few words about neighbor discovery. A neighbor discovery protocol is basically a set of mechanisms that are covering a bunch of problems that are solving, that are helping in link local communication. IPv6 nodes basically use neighbor discovery to find out about each other's presence on the link, to find out link layer addresses, link parameters like MTU, or for example internet parameters like hop limit count, and also to find out information about routers on the link, and to verify the information about reachability paths to active neighbors. So mechanisms that neighbor discovery consists of are router discovery, that's basically the process in which routers advertise their presence on link. Prefix discovery, that is related to router discovery and involves communication between routers and hosts, and is the process in which routers inform nodes on the link about set of IP ranges that define on-link prefixes. Parameter discovery is similar, just that routers inform hosts about link parameters and internet parameters, such as already said, like MTU or hop limit count. Then address resolution, which is basically the same thing as address resolution protocol in IPv4, plus some improvements and optimizations. Then we have next hop determination, that is some kind of algorithm of mapping destination address into next hop address, which can be either router address or destination neighbor address. Then we have neighbor unreachability detection, that is a process used by nodes when they have to detect and try to solve the problem when their host, when their neighbor that they're talking to is no longer available. That was in IPv4, we had something similar with that gateway detection mechanism, but neighbor unreachability detection solves bigger set of problems. And we have redirects that I've already mentioned with IPv4, when the host has to choose alternate best hop route to the destination. All these mechanisms that I listed on the previous slide, they're supported to the use of 5 ICMP messages. We have neighbor solicitations. They're sent by nodes when they want to find out a link layer address or just to verify the cached information that they have about their neighbors. We have neighbor advertisements that are basically responses to neighbor solicitations, so they contain the answer to the query. Neighbor advertisements don't necessarily have to be sent as a response to neighbor solicitation, that they can be sent as unsolicited messages. For example, when the node is about to change the address, which is, for example, suitable for mobile nodes, as announcement of the change. And we have redirects that participate in redirect mechanism that I mentioned on the previous slide. And we have router advertisements that are used by routers in router discovery process, and when routers are sending prefix and parameter information to hosts. And we have router solicitations, because router advertisements can be sent either periodically or as a response to router solicitations. When it comes to BSD implementation of neighbor discovery stack, there is difference between first 3 messages and the last 2 messages of the slide, because neighbor solicitations, advertisements, and redirects, they're handled completely by neighbor discovery stack in kernel, while router advertisements and router solicitations, they're partially handled by daemons, router advertisement daemon and router solicitation daemon. Basically, their output functions, output routines are implemented in those daemons. I wrote on the slide the example of router advertisement daemon configuration file. So if we want, for example, to set up that the router is sending router advertisements on M0 interface, router advertisements each 10 seconds, then we just have to write something like this. And a similar is configuration file for the router solicitation daemon. I mentioned this difference between these messages because I'm going to talk about it later when talking about my implementation. The problem with both with neighbor discovery and IPv4 link local communication protocols is that if they're not secure, they are vulnerable to certain set of attacks. And I have an example of two attacks, so this slide and the next slide. They're the most typical attacks. The first one is, the problem is that anyone can steal IP address. So if a node sends neighbor solicitation, attacker can easily answer with its own link layer address. And that's perfectly fine with the protocol. There is no way to detect this problem. The second problem is the one that I've already mentioned in the first slide, and that's the router impersonation. So if attacker connects to the link and it can send a router advertisement and easily trick nodes into thinking that that router is authorized to act as router on the link. And as a consequence, router can do basically whatever he wants, either to redirect traffic to someone else, send wrong parameters, send wrong prefixes, whatever he wants. And if we take a look at those attacks, there's actually not much brainstorming needed to come up with those attacks, and which is even worse, there's much effort needed to perform those attacks. And that's basically because neighbor discovery, and it's the same thing with IPv4 mechanism, they lack for essential protection. There is no authentication, no integrity protection, and they don't provide any authorization capabilities. But they have some basic protection shields, like neighbor discovery has some basic protection shield. For example, one of the things that it does is that it puts restriction on hop limit count to be 255 to prevent source address spoofing coming from the outside of the link, but that's far from being enough to solve other problems that I showed in previous slides. Initial proposal for neighbor discovery protocol was to use IPsec, but basically because the protocol was written at a time when many people would just, when it came to writing security section in IETF document, they would just just use IPsec. But it's turned out that IPsec approach is really problematic, especially because it simply doesn't work with ICMP, because if we use IPsec with daemon, IK daemon, then we end up having bootstrapping problem, because ICMP needs security association. It has to be set up with IK daemon, and it's the same thing the other way around. IK daemon needs ICMP in order to resolve the jest, so we end up having chicken and egg problem. But even if we decide not to use IK and just have a static exchange of keying material and static security association setup, then we bump into the next problem, and that's the problem that IPsec databases are linear, and in the case of ICMP we would have a huge number of records, both security association, security policy records. It's not only that we need 2 times more security associations than the number of neighbors, but also there's some multicast addresses that would have to be in security policy databases. So we would just end up having a huge number of records, and the whole thing wouldn't scale well. But even if we decide to agree that it would take ages to use IPsec with ICMP neighbor discovery, what IPsec lacks for is our authorization capability. So with the use of IPsec authentication header, we will just solve a small subset of problems. So obviously, IPsec is not a solution, and that's why people came up with secure neighbor discovery It's important to point out that secure neighbor discovery is not a new protocol. It's just enhancement to neighbor discovery protocol. That's the enhancement that is offering 3 important new features that are listed here. That's the proof of address ownership, message protection, and router authorization. I'm going to say a few words about those 3 features on the next slides. And enhancement is achieved basically through the use of 2 new messages that are send specific messages. So they're, for example, in BSD, they're not implemented in neighbor discovery stack, but they're usually exchanged directly between SeND user and the daemons. And through the use of 4 new NTP options that are just added to prepend it to the end of those 5 neighbor discovery messages that I mentioned before. Okay, so those 3 new features that I've mentioned. The first one is the proof of address ownership. So I'm just going to say a few words about how we can achieve the proof of address ownership. The whole mechanism is based on CGAs. CGA stands for cryptographically generated address. And cryptographically generated address is basically just IPv6 address with a small difference to the usual address that the last 64 bits are generated in a cryptographic way. So we generate the interface identifier as a one-way hash of the prefix, link prefix, public key of the sender, and some other auxiliary parameters. And in that way, we make a strong binding between IPv6 address and sender's public key, and that's how we provide security. On BSD, we generate CGAs with cgatool. cgatool was originally developed by DoCoMo entity some time ago. And here's the example. Like, we can just say the length of keys that we want to use, and the prefix, which is 2000, and we just, the output file are CGA parameters. These are parameters that are sent as a part of neighbor discovery to the other node, so that the other node can recompute the interface identifier to verify that the hash is fine, that the hash is matching. But someone might ask, what kind of protection does CGA provide? Because public key is just public key and it's available to everyone. Well, the thing is that security is actually achieved through the when the sender asserts the knowledge of the private key, and that's something that he does in neighbor discovery message. I'll show that on the next slide. And then the next question that people usually ask is, okay, we'll assert the knowledge of private key, but again, public private key pair can be generated by anyone. So what is this all for? Why do we need all this? Well, the thing is that CGAs don't deal with non-repudiation. They don't. The problem that they deal with is when someone is already using the IP address, they make sure that no one can steal that address. So the protection that it gives to us is that if we are already talking to someone, we can be sure that the person that we are talking to is still the same as the person that we talked to in the last message. So that's basically what CGAs does. And there's already the problem that I showed on the first slide with those 2 slides with the text. The next feature that I said that SeND is providing is message protection. So we basically, there's in neighbor discovery protocol, there is SeND enhancement, that is the RSA option, and that's basically public key digital signature inserted into the message, and it's produced with a private key that matches the public key used in CGA generation, and that's and the signature is made over link layer addresses, IP addresses, and neighbor discovery message, and that's how we end up having strong binding between IPv6 address and lower layer anchor. So we actually have binding sender's public key, IPv6 address, lower layer anchor, which is pretty safe. So with this SeND option, we get authentication and integrity protection of messages sent to the other node. And then the third feature that I've mentioned is router authorization, that is supposed to fix the problem of router impersonation of the link. And that's achieved through the use of PKI certificates at the moment, but there are new jobs that are actually using our PKI certificates. But I'll not go into details about this. So what happens in router authorization is that router sends to host a certificate chain that starts with router authorization certificate that contains the on-link prefixes that router is advertising to nodes, and the chain goes through middle certificates to the trust anchor, and trust anchor is the same that the host is configured to trust. So that's how they achieve trust. And then when the node receives such message certificate chain, the node knows that the router is really authorized to act as router. And it also knows the second thing, that the router is authorized to advertise certain set of prefixes. And trust into the set of prefixes is achieved through the addition of new extension to standard PKI certificate. That's IP address extension. That's basically just extension that contains IP range that defines the on-link prefix. On BSD, we have ipexttool that is again developed by the DoCoMo entity. ipexttool is used to, so what we do is that first we generate, when we want to configure a router to participate in router authorization process, we generate just usual PKI certificates and then add IP address extension, that's RFC 3779 extension. And here is the example of the configuration file that ipexttool is using when producing such extension. So we just have to say the prefix, and then we're saying on the files section, we're saying what is the trust anchor and where is the key located. So basically what we need for what the certification authority needs in order to do something with the certificate. And then we just generate certificates. It's pretty simple. And the second thing, so I said router authorization is about authorizing router to act as a valid router, and the second thing, to authorize router to advertise certain set of prefixes. So ipexttool also does on the previous slide I said about the authorization of prefixes, and on this slide it's authorization of the router itself. So we just basically need a configuration file. In the configuration file on router we list the whole chain of prefixes that router is supposed to send to host, and what host means is just the configuration that is saying this is your trust anchor, that's something that you'll use to achieve trust with the router. Okay, the SeND implementation that exists for BSD was developed by DoCoMo entity, and cgatool and ipexttool are coming together with SeND daemon implementation. They developed implementation for both for Linux and FreeBSD. On FreeBSD, here is the picture of how the whole solution works. So, since SeND is basically just the enhancement of neighbor discovery protocol, what they're doing is that they're taking neighbor discovery messages generated in kernel, sending them to user end, so the daemon can do validation or to add send options, and then sending back to kernel to neighbor discovery stack again. For example, if we have the incoming message, so the incoming message will have send options prepended to the neighbor discovery message, then the message would come to ng-ether lower hook, then go to ng-bpf. ng-bpf has to decide if that's one of the messages that SeND daemon wants to deal with. And in case that it realizes that we have the message that we have to send to userland, then it sends a message to ng socket, and at the end, message ends up in send daemon. Send daemon will validate message and strip off all send options. So what we'll have at the end, before sending message back to kernel, is just pure neighbor discovery protocol message, which will be sent back to ng socket, and then to the ng socket out hook to NGBPF, and then to upper hook to upper protocol layers, and there the message will be processed as the usual neighbor discovery protocol message. If we have the outgoing message will be produced by neighbor discovery stack in kernel. And then the message will go to upper hook to NGBPF, and then it will be sent again to send user and daemon. Send user and daemon will add send options to the message, prepare to the end of the message, and then send out to ng socket, NGBPF, and lower hook out of the interface. So two major drawbacks to do a SeND API, native SeND API, was the use of netref and BPF filter in this implementation, because netref is too big overhead for this implementation, and BPF filter is as well, because all messages, but all IPv4, IPv6, all packets have to go to BPF filter. And there is a second thing beside the overhead. Netref is not supported throughout the whole BSD families, and we wanted to do something that is portable to other BSDs as well. And beside these two major drawbacks, one of my motivations to do this native API was also drafts, ITF SeND related drafts. These are going to become RFC soon, so I just wanted to do the implementation. What were our initial design decisions? They're listed on this slide. So this was obviously to avoid the use of netref and of the use of BPF, as I have said on the previous slide, because we wanted to process only packets affected by SeND, just to lower any overhead. Then one of the design decisions was also to trigger SeND only if SeND code is loaded, which means that we decided to put our code in a kernel module, and in case that module is loaded, SeND will be triggered. In case that module is not loaded, we'll just use pure neighbor discovery protocol. One of the decisions was also use routing sockets to send neighbor discovery messages to userland and back, mainly because in the first step we decided to do to make the code to be as simple as possible, and the simple thing was to use routing sockets. It was also due to one of our decisions that we wanted to reduce the number of the lines of code, so we were reusing the code that was used in net 802.11. They're using the same thing, sending messages to userland and back. So we reused some of the code. Then also one of the decisions was to keep separate socket for SeND-specific messages, because I mentioned before that there are two messages that are just SeND-specific and they're not handled at all by neighbor discovery stack. So we're using a separate socket so that those messages can be exchanged directly between daemons. And what I've already mentioned, add as few new code as possible, both to userland application and in kernel. So what we did is we added hooks in certain places, which means when we want to take the neighbor discovery message and send to userland, we'll do that after all possible neighbor discovery processing, and then send to kernel. And when it goes, when it goes back the other way. so this hook was the input hook, and to place the output hook at the appropriate place as well when the packet goes in the opposite direction. So we basically have input hooks and output hooks. Input hooks are placed on the way from NDP kernel stack to user and the daemon, no matter if the packet is incoming or outgoing. And output hook goes in the other way, from the user end to output interface output functions, again no matter if the packet is incoming or outgoing. The actual code is in SeND kernel module. So the SeND kernel module contains hooks and obviously dispatching logic. And what we needed also is additional code to be able to use the routing socket to send messages to user and back. This is a picture how the whole thing works. So when we have incoming send packet, we have input hook in ICMP6 input message. And then we use the routing socket, and we're sending a message to send daemon. Send daemon takes off all the send options, validates the packet, and sends the packet back to kernel. In case that the module is not loaded, we just go to ICMP6 input and end up at the same place as well. The outgoing packet, the code with the outgoing packet is just a bit more complicated because we have more places where the packets originate. Like in ND6 NA input, which is ND6 neighbor advertisement input function, we have neighbor solicitations generated there. Then we have ICMP6 redirect output, ND6 neighbor solicitation output, and neighbor advertisement output. Those are the standard functions where the related messages are shaped. And we also have what I mentioned so far are redirects, neighbor solicitations, and neighbor advertisement, and what is left are router advertisements and router solicitation, because as I've said before, they're not handled completely by kernel. So we're taking them on different places before they go to router advertisement and router solicitation daemons. And then we have again, just before sending the packets out of the interface, we have input hook that is sending packets to routing socket to send daemon. Send daemon protects the packet, so as send options and so on, and then sends the packet again to kernel, neighbor discovery, kernel stack, and then the packet goes out. What we're doing with these stacks, we're taking mbox because at the place where the hooks are placed, it's already too late to get into the packet. So the easiest thing to do is just to take the packet with, so that we know which messages we have to send to user one. So current state is what I've just said. We're using routing socket, and one of the problems with routing socket is that we're not getting any information back if send daemon crashes. So if send kernel module is loaded and if send crashes, then the node is not able to use neighbor discovery anymore because the packet will stop at the hooks, and it's obviously not able to use send daemon either. So what I'm doing at the moment, and I managed to get the code working, is native send socket, which is in a way similar to divert socket. It's just a native socket that makes sure, for example, when the daemon binds to the socket, it makes sure that's the only daemon that will be bound to the socket, and when, for example, send daemon crashes, it makes sure that the code fails back to pure neighbor discovery, so that we don't prevent node from talking neighbor discovery if he wants to talk unprotected, in an unprotected way. one of the plans when I test and finish the work with this native SeND socket is to implement my drafts, SeND-related drafts. Then one of the things to be discussed when it comes to native SeND API are patents. There is one patent related to CGAs owned by Microsoft. There's the other one, Ericsson patent, but that one is out of date because, as I've already said, it's about SeND IPsec, and IPsec is not used anymore with SeND. So basically the only problem are CGAs. And then at the end, one of the things that have to be done is interoperability testing. There was interoperability testing organized actually next weekend, just before ITF meeting, but there's still not enough implementation. So there was basically, I think it was organized by Cisco, and there was no one else applied, and I'm obviously here, so probably at some future ITFs that there will be interoperability testing again. The code is available in my Google Summary of Code branch. The code that is at the moment there is the code that is using routing socket, and in a few days I'll submit new code with native SeND socket. There's also a patch that, because in branch you'll get just, of course, kernel patch contains both the user and daemon, ipexttool and cgatool. So feel free to download it and contact me if
you know, the IPR issues with Ericsson and Microsoft, have they offered any reasonable terms, as in reasonable as in don't sue us and we'll get IPR? Or?
Yeah, I don't know much details about patents, so I take a look in the morning, and I'm still not aware of the actual problems. Maybe they're even not. Maybe there are even no problems, but yeah, I'm not sure at the moment. Anyway, the project was sponsored by Google and also FreeBSD Foundation, so thanks to them. And if you have any questions, yeah.
So this might be covered in the paper, but doesn't this require the pre-sharing of a large number of keys to make your network work correctly now?
No, there's no sharing of keys.
If I connect a new computer into if I connect a new IP600 into my network, what do I have to tell it to make sure that it receives the correct server?
Well, if you're just a node, you have to generate CGI-JS, configure your interface with CGI-JS. So you will generate public-private key pair, but what you're sending to your host is your public key in CGI parameters, and that's one of the NDP options, actually SeND options. So there are no pre-arrangements.
Okay.
Yeah. The only thing that has to be pre-arranged is that hosts, if they participate in route authorization, that they're aware of just anchors. That's the only thing that has to be pre-arranged in case of using certificates, so that they can validate certificates chain.
Okay, so basically for them to accept the router advertisement,
yes,
they need to have some setup.
Yes, they have to trust to the same trust anchor as router trusts. So,
okay.
Yeah. Any more questions? Maybe? Yep.
I don't know well about the kernel motion mechanism of BSD, and your design looks like dependent on a FreeBSD mechanism of kernel modules. And how about the portability to NetBSD and OpenBSD?
Well, yeah, at the moment, but it's I guess that's one of the things that is easy to fix. I think the biggest problem was to switch, to move from the use of Lasergraph. That would definitely prevent us from porting a solution to any other BSD.
Yeah, and your implementation is in post-correction?
Sorry?
Post-correction on your implementation.
No, it's available only in branch. There is a patch online.
That only?
Yeah.
How about make polls?
Well, the first thing that has to be discussed is those patent issues, and after that, it's I'm free to do all these things.
Yeah.
Maybe maybe other questions? Okay, thank you.